Welcome to my lecture series on gate maths. Now we are on the fifth video, and here I am going to take you the special matrices. Special matrices. We have seen the types of matrices, right? That is square matrix, upper triangular, lower triangular, diagonal matrix, scalar matrix. All we have seen, right? Likewise, there are some special matrices. That is what we are going to see now. First one, symmetric. Next is skew symmetric. These both are somewhat similar. A symmetric matrix is one that has A is equal to A transpose. So what is a transpose? Those who doesn't know this, please check on to my previous video. I have made a lecture on this. Okay, transpose, conjugate, everything I have made a lecture. And just a recap, A transpose means interchanging the rows and columns. That is what we say as A transpose. A transpose is equal to A. That is a symmetric matrix. Then how the matrix should look like? 1, 2, 3, 2, 5, 4, 3, 4. See, however you interchange the rows and columns, this won't change. Okay, let's check it now. A ij will be equal to A ji. That is what we call a symmetric matrix. This is A11, A12, A13, and this is A21. See here, Aij, A12 is equal to A21, right? This is what we call as symmetric matrix. If you interchange and write, you will get the same thing. And what is skew symmetric? A is equal to minus A transpose. So let A be a matrix. A is equal to 0, 2, 3, minus 2, 0, 3, minus 3, 0, 4 we will take it. This is 4, minus 4 and 0. In this matrix, it will be Aij will be equal to minus Aji. That is A12 will be equal to minus A21. See, A12 is 2 here, and this is A21 is minus 2. This is called a skew symmetric matrix. And one more thing, what you have to remember in a skew symmetric matrix is all the diagonal elements, principal diagonal elements will be 0. Check it here. The principal diagonal elements will be 0. Next, we go to unitary matrix. Sorry. A theta into A is equal to I. A matrix is called as unitary matrix. If A theta into A is equal to I, what is A theta? A theta is the transpose conjugate matrix. Transpose conjugate of a. Please check on to my last video for a detailed explanation about this matrix. Okay. And another thing is what? A theta is equal to A inverse. These are the two properties of this matrix. And the next one is Hermitian matrix. A matrix A is said to be Hermitian matrix if A is equal to A theta. That means transpose conjugate of a matrix will be equal to the matrix that is called as Hermitian matrix. If A is equal to A, B plus IC, B minus IC. This I is what? I is this one represents the complex number. B plus IC and B minus IC is the complex number. So now what is this? A should be equal to A theta. A theta means transpose conjugate. You have to find the transpose and you have to make it as a conjugate. Okay. So now we find A theta. A theta is equal to, first we'll write the transpose. Transpose means what? First row should be the column here. Okay. A, B minus IC. I have written transpose first. Now you have to make it as a conjugate. Conjugate means you have to change the sign of the complex number. Here the sign of the complex number is minus, so we have to change it to plus. And next one, this is the second column here. You should make it as a row. So B plus IC, and these are the two elements. Now that B plus IC, we should change the sign as B minus IC. This is called as transpose conjugate. So A is equal to A theta. If a matrix is like this, we will call it as Hermitian matrix. And the Hermitian matrix will be real if the diagonal elements are real. So here the diagonal elements are A and D. It is real, so it is called as real Hermitian matrix. Next is skew Hermitian matrix. Skew means it will change the sign. It will be negative. Okay. A is equal to 0 minus 2 plus I, 2 minus I, 0. Now what you have to find is A is equal minus A theta. A is equal to minus A theta. So you have to find minus a theta. You have to find the transpose first. This column I am writing as a row. So I am making the conjugate here, minus 2 plus I. And next row I will make it as a column here. So after making the conjugate, it will become 2 minus I, 0. See, these both are equal, a and minus a theta. So this is called as skew-Hermitian matrix. And the skew-Hermitian matrix will be purely imaginary. Next is orthogonal. A into A transpose is equal to I. That is, A transpose is equal to A inverse. This is an orthogonal matrix. This is a condition for orthogonality. And this is an important thing that you have to remember. You will get problems in this. And I have made an example problem for this. Idempotent matrix. Idempotent matrix means A squared is equal to A. Involuntary matrix. Involuntary means A squared is equal to I. Nilpotent matrix. A to the power m is equal to 0. When you square or triple or quadruple anything you do, the matrix will become 0. That is called as nilpotent matrix. And the final one is permutation matrix. This matrix will consist of only zeros and ones. And the determinant will always be plus or minus 1. So these are the some special matrices. Let me recall you. Symmetric matrix, skew-symmetric matrix, unitary matrix, Hermitian matrix, skew-Hermitian matrix, orthogonal, idempotent, involuntary, nilpotent, and permutation matrices. First one, skew-symmetric, A is equal to A transpose. A matrix that is equal to its transpose is called as a symmetric matrix. And a matrix that is equal to its transpose in a negative, it is called as skew-symmetric matrix. And A theta into A is equal to I. That gives you unitary matrix. Hermitian matrix is A is equal to A theta. Transpose conjugate. A theta means it is transpose conjugate matrix. Skew-Hermitian, A equal to minus A theta. Orthogonal is A transpose is equal to I. Idempotent matrix means A square is equal to A. Involuntary means A square equal to I. Nilpotent means A to the power m is equal to 0. Permutation matrix means the matrix that consists of only zeros and ones, and its determinant is always plus or minus 1, and it follows that A transpose is equal to I, and it is an orthogonal matrix. Now let's see a problem in an orthogonal. The matrix A is equal to L 0 sin theta 0 1 m and 0 cos theta is orthogonal if they have given you a matrix A that is orthogonal, and what you have to find is on which condition it is orthogonal, that we have to find. So what is orthogonal matrix? A transpose is equal to I. So what is A here? L 0 sin theta 0 1 m and 0 cos theta. It is A transpose. L 0 1 0 1 0 sin theta m cos theta. This will be equal to I. 1 0 0 0 1 0. Now let's make a multiplication here. Square plus 0 plus sin square is 0 plus 0 plus m sin theta, nn plus sin theta into cos theta, m sin theta 1 plus m square, m cos theta plus sin theta cos theta, m cos theta, n square plus cos square theta equal to I. 0 0 1 0 0 0 1. Now let's simplify. We'll equate it. So L square plus sin square theta equal to 1. 1 plus m square is equal to 1. M square plus cos square theta equal to 1. Sin square theta is equal to 1 minus square equal to cos square theta. L equal to plus or minus cos theta. M is equal to 0 here. N square is equal to 1 minus cos square theta. N square equal to sin square theta. N equal to plus or minus sin theta. So the condition on which the two matrices will be orthogonal is these values L, M and N. Let's check the answer. So the answer will be D. Why? L equal to minus cos theta, M equal to 0 and N equal to sin theta. When you take this, the answer will be orthogonal. Now let's check out some properties of these matrices. These special matrices have some properties, and these properties will be asked in one word. A is a symmetric matrix, that means A equal to A transpose. Means minus A is also symmetric. So that means what? Minus A will be equal to minus A transpose. Ka is also a symmetric matrix. A transpose is also a symmetric matrix. And A to the power n is also symmetric matrix. A inverse, B transpose, AB. These all are symmetric matrices. A transpose into A is also a symmetric matrix. A into A transpose is also a symmetric matrix. A to the power 2n is also a symmetric matrix. And if caps, if A, B, A and B two are symmetric matrix, then A plus B is symmetric matrix. AB plus BA is also a symmetric matrix. AB equal to BA is also a symmetric matrix. These how they will ask you is, the question will be like this: if A is a symmetric matrix, which of the following is also a symmetric matrix? Like this, they will ask a question. So these things are also symmetric. Next one, we'll see skew symmetric. If A is a skew symmetric matrix, skew symmetric means A will be equal to minus A transpose. Then Ka is also skew symmetric. A to the power 2n plus 1 here. Here A to the power 2n and A to the power n are symmetric. Here A to the power 2n plus 1 is symmetric. B transpose AB. If A and B both are skew symmetric matrix, then AB minus BA will be skew symmetric. Here AB plus BA is symmetric. Next, A minus A transpose will also be skew symmetric. Then it means here A plus A transpose will be symmetric. And another thing, if A is a skew symmetric matrix and C is a column matrix, which of the following will be true if they ask? Then C transpose AB is 0. Let me say, if A is a skew symmetric matrix and C is a column matrix, then C transpose AC will be 0. Another final quote: every square matrix can be uniquely expressed as a sum of symmetric and a skew symmetric matrix. That is, if A is a symmetric matrix, then this matrix can be written as A plus A transpose by 2 plus A minus A transpose by 2. See here, A plus A transpose is a symmetric, right? This is symmetric. A minus A transpose is skew symmetric. So what is the theorem I said? Every square matrix can be uniquely expressed as the sum of symmetric and a skew symmetric matrix. This is what we have completed. See, on the roadmap, now we have completed this matrices and determinant part. I have completed the classification of matrices, algebra, properties and special matrices. See, on the classification part, we have seen all these things: square matrix, diagonal, scalar, unit, triangular and null matrix. On the algebra part, we have completed all these operations, and the properties of matrices we have seen, and all these special matrices also we have seen, and we have seen few problems. These problems are previous year asked questions. These have been asked in various departments, not only in the aerospace, it has been asked in other departments also. I have compiled everything and I have made this video. In the next video session, we'll be seeing this determinant and we'll go to the system of linear equation. Keep watching. Thank you.